All right, guys, what I want to do here is just recap the major points of what you learned in chapter one. It's very easy to get lost in the details and not realize, the big picture, what you've actually learned here. So, big picture, chapter one, the question was, what is a limit? The easy answer to what is a limit is if you have a function, right? The limit is the y value that that function approaches at some particular x value, right? The short answer to what is a limit is the y value that the graph approaches. And what we looked at were different ways that we could find that y value because it wasn't always straightforward, right? The first way that we looked at that you can find that y value is numerically, right? This is where you make your table and say you want to find the limit as x approaches 1. You have to choose values that get closer and closer to 1. So say I choose, 1.1, 1.01, 1.001, and then on the other side of that, zero point 0.9, 0.99, 0.999. And you have to have a calculator to solve these problems and work with those ridiculous decimals. But what you're looking for is what number are we getting close to the left and the right? If those numbers don't match, then we know that the limit does not exist. If those numbers match, then we can say what that limit is. So there's numerically, and that's when you have to have a calculator. We can also find limits graphically. And this is definitely the easiest, just depends on what you have available. You can draw the graph yourself, or if it's not an easy function, then you would have a calculator to be able to graph it. These are especially useful for piecewise functions. So say you have a function that looks like this. That was a terrible piecewise function, but that's fine. And then let's say you want to define the limit as x approaches this value right here. Well, from the left, it approaches this y value. From the right, it approaches a different y value. So I can say with confidence this limit does not exist. The left limit and the right limit exist, but the overall limit does not exist because the left and the right hand sides do not match. So we've got numerically, we've got graphically. Typically, you have to either be given the table, given the graphs, or you have to have a calculator for those problems. And here's the big one. We can also find limits analytically. This is where you don't have the calculator, but we've got a whole bunch of tricks up our sleeve. So within this category of analytically finding limits, the easiest one, and this should always be your go-to, the first thing you should try is direct substitution. And this is where if you've got, f of x and you want to find the limit as x approaches 2, the first thing you should always try is just plug in 2. If you plug in 2 and you get some number, then you have found the limit. You have found the limit by direct substitution. That's the dream. You move on, right? Uh, if this doesn't work, if plugging in the value of c, if plugging in that value makes you have something that's indeterminate, something that's undefined, 0 over 0, something like that, that's when you start looking for a way to rewrite the function. Is there a way that I can rewrite this function that gets rid of a discontinuity that'll let me then plug in the value and use direct substitution? And so here's where you have your tricks. Your tricks are that you can factor it, and yet factoring can get complex, right? You might have to try long division, synthetic division, um, but you should always try that first. See if you can factor it. Factor the top and the bottom, see if a factor cancels out. If that doesn't work, try multiplying by the conjugate. This is when you have, x plus some number, and you multiply top and bottom by x minus that number. And oh, by the way, your clue for that is that your number is probably in a square root. That's when multiplying by the conjugate works very nicely. So you've usually got, x plus some radical over x. There may be another number here. That's fine. But then you multiply top and bottom by that conjugate, and that's going to get rid of the square root. Something's going to cancel nicely, and the problem's going to work out for you. And then the other thing you should be on the lookout for is your special trig limits. Don't forget those two trig limits that you should have memorized. And that's a good way to rewrite things. Don't forget your ratio identities. Um, Say, you can rewrite tangent of x as sine over cosine. That's a big one. Same thing with cotangent, rewriting it as cosine over sine. Usually you can do a trick like this and then go use one of the special limits to simplify a trig problem. Okay. Um, we have those limits where x isn't just approaching a number, but what about when x approaches infinity? And this is where you need horizontal asymptotes. If you're looking for a limit as x approaches infinity, that's when you're following the horizontal asymptote rules. So that's where, if you have a fraction, so you have y equals x to some number and x to some number here. And I'm just looking at the highest powers, right? If the top number is bigger, also meaning there's no denominator, right? No denominator would fall into that category of the top being bigger. Then there's no horizontal asymptote, and so the limit as x approaches infinity is infinity. If the bottom number is bigger, then y equals 0 is a horizontal asymptote, and so the limit as x approaches infinity is 0. If these numbers are the same and you have some coefficients out front here, then the horizontal asymptote is the fraction of those coefficients, and that's also your limit as x approaches infinity. Okay, so if you have x approaches infinity, follow your horizontal asymptote rules. If your if you have vertical asymptotes, right? So if you have horizontal asymptotes, that tells you about the behavior as x goes to infinity. If you have vertical asymptotes, these result in infinite limits, right? So the answer to the limit as x approaches to, the answer will be plus or minus infinity if you have a vertical asymptote. So this is always where you're looking for places where the denominator is equal to 0. That's what's going to result in vertical asymptotes. Your graph will look something, maybe like this. And I can see that I have a vertical asymptote here at 0. Vertical asymptote at x equals 0. So if I'm just looking for the limit of f of x as x approaches 0, I can say that that does not exist, right? Because the limit from the left does not equal the limit from the right. But I could find each of those individually, right? If I were just looking for the limit as x approaches 0 from the left, then I can see that that's going to be negative infinity. If I wanted the limit as x approaches 0 from the right, that would be the positive infinity. And we know that technically infinite limits aren't real limits, right? It's got to be a finite number to be a limit. But if it asks you to find the limit from the left or right of something with a vertical asymptote, this is a valid answer, right? And once again, the multiple choice is never going to ask you to choose between does not exist and infinity, right? You would not see both of those answer choices. It would just be one or the other. They're not trying to trick you with that. I'm not trying to trick you. While we're here, let's talk about this idea of continuity. Continuity is a big part of this chapter because up to this point in your life, continuity meant you can draw it without picking up your pencil. But we have a very, very precise definition of continuity using limits. That definition has 3 parts. First part says, that the function at a particular value is defined. All this means is there's not an asymptote there, right? That's what the first part of continuity means, is that there's no asymptote at this particular point. Second part is that the limit as x approaches c of f of x exists, right? So we're just saying that the limit from the left matches the limit from the right. The limit does in fact exist. And then here's the thing, the third part is that whatever value 1 and 2 are, those values have to be the same. Parts 1 and 2 have to be the same number. So we've looked at illustrations of this before. So say you have a function that's got a hole right here, and then it's defined somewhere else. It meets the first requirement, it's defined. It meets the second requirement because there is a limit there, but it fails the third requirement because these are not the same value, right? It has to be, the limit has to match the definition in order to have this definition of continuity met. We take continuity for granted, but it's the first criteria that has to be met before we can solve any other calculus problems. When we get to derivatives, there's always this caveat of the function has to be continuous at the point that we're looking at. Um, and here's the other point of discontinuities too. Is let's say you have a nice, well-behaved function, and then you get a discontinuity, right? You can do calculus, you can do all those problems here, you can do all those problems here, you just can't do them right here, right? So discontinuities tell us where we can and can't do the rest of calculus, where we can integrate, where we can take derivatives, things like that. Okay, and then of course we had those two theorems, intermediate value theorem and squeeze theorem. And I wouldn't even worry about those while you're studying for the test. You've been exposed to them, you know what they are. That's all I wanted to do on those.